In this video, we're going to solve a problem taken from the IMO long list. We are given real numbers x, y, and z with sum equals to 3, sum of the cubes equals to 15, and sum of the fourth powers equal to 35. Find the value of the sum of the fifth powers. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. There is actually an extra condition in the original problem, which is that the sum of squares of these three real numbers is less than 10. So I'm just going to focus on this case. Now, for these real numbers x, y, and z, I'm going to consider a cubic equation with these three numbers as the solutions, the roots. So let x, y, and z be the roots of some cubic, say let's call that a cubed, and then for the coefficients I'm going to say let p, q, r be the coefficients, just some constants p, q, and r for the time being. Then we know that to have x, y, z as the roots, then the equation at the left is equivalent to saying that it can be factorized as a minus x multiplied by a minus y multiplied by a minus z. And if you expand and compare coefficients, you can see that for p is actually equal to minus of their sum, x, y, and z, while for q is actually xy plus yz plus xz, while for r is minus xyz. So I'll just write these expressions at q and r for the time being, and then for p I can say p equals minus 3. Now further from the cubic, I can replace the unknown a in the equation by x, y, or z. By doing so, I'll have a relation on x, which is x cubed minus 3x squared, and then for q it's just, I'll just put it as q for the time being, qx plus r equals 0. And from this, I can tell that x cubed can be degenerated into smaller powers of x, because we are given that the value of the sum of cubes. So 3x squared minus qx minus r. And I can do similar things on y and z. And for z cubed, it's an equation of similar form. And so if I add them up, I'll have 3 times the sum of squares minus q times their sum. We know that's 3, but it's not that important at the time being. And then minus 3r. So in that case, I can degenerate the sum of powers into smaller, sum of smaller powers. Further from this, I can multiply x, y, z, and even powers of that into each of these three equations. Say if I multiply x to the power of n on both sides of the first equation, then for the left we have x to the power n plus 3, and then we have n plus 2 over here, n plus 1 over here, and r times x to the power n. Similar for y and for z. And from this, we can actually make this relation on sum of arbitrary powers of x, y, and z. But now be careful that we are not we're not having 3r, we're having r times the sum of n powers. It's just that for the cube case, we have r times x to the power 0, y to the power 0, z to the power 0, and they are all 1. So then we have 3r at the end. And so this is what we're going to get if we were to relate the sum of powers of x, y, and z. And to make things look easier, I'm going to let, say, for any non-negative integer, Sm equals the sum of the m powers of x, y, and z. And we actually have plenty of information from on these terms. Say S0 is 3, S1 is 3 is given, S2 is still unknown, but we'll find it out soon. S3 is 15, and S4 is 35. And for our problem, we're just asked to find value of S5. Of course, we can specify that S2 is less than 10 as well, although the actual value is still unknown. So from the equation above, we can say Sn plus 3 equals 3 times Sn plus 2 minus Q times Sn plus 1, and then minus R times Sn. And now we can put any non-negative integer into n, and then we can get lots of relations on these s terms. For example, when n equals 0, that's just what we've got above. On the sum of cubes, we will have 15 equals 3 times s2 minus q times s1, and that's 3q minus 3r. Simplifying, we will have 5 equals s2 minus q minus r. Of course, we can say something about s2, and all we know about that up to now is I can say s2 is s1 squared with an extra 2xy, 2yz, 2xz, but if you add them up, that's q. So we just subtract 2q. So I can say S2 is equal to 9 minus 2q. And put it in and say 5 equals 9 minus 2q minus q, so that's 3q minus r. So 3q plus r equals 4. That's what we can tell once we put n equals 0. Very simple. Now if we put n equals 1, then we have S4 on the left, which is 35. 35 equals 3 times S3. Now that's 45, 3 times 15. And then minus Q times S2. And then S1 is 3, so minus 3R. And so we have Q times 9 minus 2Q plus 3R equals 10. And 9q minus 2q squared plus 3r equals 10. And you may notice that for the first and the second equation, the labeled terms are actually multiples of one another. So you can just put the first equation into the second by multiplying the first equation by 3. So if I label them, I can just say multiply the first one by 3 and then minus the second one. I'll only get 2q squared remaining on the left, and for the right we have 2. So q either equals 1 or q equal minus 1. Then you can say when q is 1, then S2 is 9 minus 2q. You can recall it from the green block. You have 9 minus 2 times 1, and that's 7. For the other case, it's actually 11. So I'm going to reject the q equals -1 case for the time being, but of course you are free to continue work it out. Say what happens when q equals -1 as an algebra exercise. I believe it's going to be quite interesting. Now when q equals 1, we can quickly say that r is, just look at the first equation, 3q plus r equals 4. Then you will have 1. And then if q is -1, then r is 7. So now we have sufficient information on finding our final answer, which is S5. To do that, I'm just going to replace n by 2. Then I can say that S5 is 3 times S4 minus q times S3 minus r times S2. So looking at these solutions, you can put them into the equation at S5. So we have 3 times 35 minus q, which is just 1. S3 is 15. And then r is 1 again. And then multiply by, minus by 7. And so you have the final answer, which is 83. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.